Hello everybody, I'm going to be showing you how to draw phase lines in differential equations. It's the first chapter. I'm using the a Wiley book. It's my first go at it, so bear with me. Okay, so we have this dy over dt equals y squared times y plus 1 times y minus 3. So what we know is that dy of dt is actually equal to y prime, right? So if it's equal to y prime, they're the same thing, they're just different notations, right? So what we're going to do is we need to find equilibrium points. So to do that, we know from calculus 1 where y prime equals 0, there's an equilibrium point, meaning it's going to go, it's never going to touch that point because there's a 0 there, right? So we're going to find all the zeros of this. So we know that there is a 0 at y equals 0, because when we plug y equals 0 in, y prime is going to be 0, right? So we know that there's a 0 at y equals negative 1. We plug negative 1 in, it's going to go to 0. We know there's a 0 at y equals 3, right? So we're going to come over here, and I'm going to say that all the points that we need on this number line, we're going to do a number line test. So we'll have 0, negative 1, and 3. And based upon which numbers we plug in on these intervals will tell us if it's increasing or decreasing in that range. So let's plug in y equals negative 2. So we'll plug it in here, we get a positive, because any squared value that is negative turns positive. Plug it in here, and we see that we actually do get a negative. Negative 2 plus 1 is a negative. And then negative 2 minus 3, that's going to be another negative. So these two become positive, and then it's multiplied by a positive, so we know it is increasing between negative infinity and negative 1. So now let's plug in a point between negative 1 and 0. And we'll just choose the simplest value you can, I guess 1/2. So 1/2 squared is a positive. Negative 1/2 squared becomes a positive. Negative 1/2 plus 1 is a positive. Negative 1/2 minus 3 is a negative. So this is a negative value, so we know it's decreasing between negative 1 and 0. So now let's plug in a value in between 0 and 3. So we'll just do 1, it's the simplest one. So 1 squared is 1, right? So 1 plus 1 is going to be positive. Positive 1 plus 1 is 2. 1 minus 3, that's a negative. So we're going to have a negative right there. And then 3 on, so we'll plug in 4. Basically, that last term just becomes positive, so we have a positive from 3 to infinity. So now this is going to be what tells us where it is increasing or decreasing, right? So we won't draw the graph just yet. We still have some more stuff to do. We're looking for. I'm gonna run out the steps. So one would be find intervals of increasing and decreasing, right? So we've done that. Now we need to find the inflection points, and to do that, in calculus 1, we know that you have to take the second derivative of a function to, we need to find y double prime basically in order to tell us what the inflection points are. So here I'll write to find inflection. And in order to do that, we're going to have to use implicit differentiation, right? Because we have a y prime, and then we have that in terms of y. So in order to find y double prime, what I'm going to do is actually I'm going to switch this, and I'm going to write this as y prime, right? So when we do that, we need to, in order to take the second derivative, we're going to have to use implicit differentiation. So we'll say, we'll rewrite it in terms that are a little more simple. So y prime equals, let's go ahead and keep this y squared, and then we're going to FOIL this. So we'll say that this is y squared, because this times this. That's positive 1y, and then negative 3y, right? So that's going to give us minus 2y, and then minus 3. Right, okay. So now let's go ahead and distribute this y squared. So now we have y to the fourth, y prime equals y to the fourth minus 2y cubed minus 3y squared. Now we're ready to take the second derivative. So in order to do this, we can say y double prime is equal to, and if you remember implicit differentiation, all you do is when you have a term of y, you have to use the chain rule. So you tag on another y prime, right? So we have, take the derivative of this, 4y cubed y prime, right? Minus 6y squared, right? Y prime, and then minus 6y y prime. Okay, so that's looking pretty good so far. So now what we're going to do is we're going to kind of simplify it and get it in some terms that are a little bit better. So y double prime equals, well, we can factor out a 2 from each of the coefficients. We can factor out a y, a regular y, from each term, and we can also factor out a y prime. The reason we're doing this is because we want to factor out that y prime, because we know what y prime is. We know that y prime is equal to this, right? So we're going to factor out a 2, a regular y, and a y prime, and then we are going to write the rest of it. So 4y squared, or sorry, that is a 2y squared. 2y squared minus 3y, and then minus 6, right? So I'm going to go ahead and erase this, give me a little more room. And now that we have this, these are going to be points of inflection that is going to be kind of like ugly because they don't, oh, sorry, minus, is it minus 3? Yeah, minus 3. So these are going to be points that are kind of ugly because they don't factor very nicely. You're going to have to use the quadratic equation, so we'll go ahead and do that first. So we have negative b, so it's going to be positive 3, negative 3 is positive 3, plus or minus the square root of b squared, 9, minus 4 times a times c, all over 2 times a, right? So what we're going to get from simplifying that is 3 plus or minus root 9 plus 8, negative 3, so that's going to be 9 plus 28, which is 33. Sorry. Yeah, 8 times 3. Yeah, 33 over 4. I might have missaid that and did something wrong, I don't know. But I know that this is right. So we're going to take, this is going to be our roots now for this part of the problem. Okay? So I'm going to go ahead and make note of that off to the side over here. 3 plus or minus root 33 over 4. So now what we can do is we're going to have to rewrite all of this, right? So we have y double prime equals 2y, and then y prime, which is equal to y squared, y plus 1, y minus 3. So this is all just this part right here, what I just wrote. And now we're going to take this and we're going to write it like this. We're going to say it's going to be y plus root, plus 3 minus root 33 over 4. I believe, let me get my calculator real quick. So if we do these roots, we get that, yeah, so 3 minus root 33 over 4 is negative 0.69. So what we're going to do is we're just going to say that this is actually y plus 0.69. Because when you plug in negative 0.69, that's when you're going to get a 0. So we're just going to kind of rewrite that when we take this test in order to make it a little bit easier. And then we have one more, which is y minus 3 plus root 33 over 4. And this is going to be equal to, it's going to be the same thing as y minus 2.19, right? So, and I know this because the 0, if this is the graph, the 0 is going to be at negative 0.69 and then positive 2.19. That's why. Negative 0.69, positive 2.19 when you plug them in. And that will give you the 0. So since I've rewritten that, I can now do an inflection points test. So in order to do this, I'm going to do the same thing I did here to see if it was increasing or decreasing. I'm just going to use this equation instead of the original one, which, granted, there's the original one in here, but there's more information we need from this. So I'm going to draw this long. Give me a second, I gotta get this pen working again. Okay. I'm going to draw this long number line right here. And we are going to test all these points, right? So we've got the equilibrium points, first of all. We need those in here because they're in the second equation. And you typically always will. So we have 0, negative 1, positive 3, right? And then instead of writing these roots like this, what I'm going to write negative 0.69 because that's where a 0 is. And I'm going to write positive 2.19. So I'll say 2.19 and then negative 0.69. Okay. So now what we're going to do is we're going to do the exact same thing we did up here. We're going to plug in some point that is between negative infinity and negative 1. So we'll pick the easiest one, right? Negative 2. And we're going to test every single one of these for inflection. I like to just write them below and remember that if you have it's important from calculus 1, I believe, is if you have a positive for an inflection point, that is a local min. It's kind of counterintuitive, right? So local min means it's going to be concave up like this. If it's a negative, you're going to have a local max, which is going to give you concave down on the inflection. So just keep that in mind, and we'll plug all these in. So negative 2, well, you know what? First, I'm just going to rewrite this really quick to make it a little bit easier. I'm going to pull this y squared out. Since this is all multiplied together, I'm just going to pull this y squared out and put it with that y. Makes things a little bit easier. So I'm going to call this 2y cubed, and then all this. Yeah, okay. So now, negative 2, well, this becomes a negative, right? So negative 2, this is kind of sloppy. This is y plus 1, but it looks like parentheses, okay? So negative 2 plus 1, that's a negative. Negative 2 minus 3, that's a negative. Negative 2, so this is where this comes into play, using decimals. I know it's not really nice to use it in pure math like this, but this helps a lot. So, because we know that negative 2 plus 0.69 is still a negative, and then negative 2 minus 2.19 is still a negative. So all these are negatives. So negative multiplied by negative becomes a positive, negative multiplied by a negative becomes a positive, and then another negative. So we're going to have a negative overall for this point of inflection, or for this interval. Oops. Wrong. Okay. So now this is kind of where it gets a little weird. You're gonna have to like plug in like negative 0.9. That's what I find is the easiest. Just like a number that's really close to 1. So we'll go ahead and do that now. So I'm gonna erase all of these because they might confuse us later on down the road. Okay. So negative 0.9. This is gonna be a negative because negative 0.9 cubed is gonna give you a negative times a positive, which is times a positive 2, which is a negative. Negative 0.9, well, this is going to turn positive this time, right? Negative 0.9 plus 1 is going to be a positive number. So negative 0.9 minus 3 is still going to be negative. Negative 0.9 plus 0.69 is going to be a negative. And then negative 0.9 minus 2.19 is going to be a negative. So okay, so negative 0.9, so these are all values for negative 0.9. So what we're going to do is we're going to, so these become a positive, these become a positive, these two right here, and they're multiplied by a positive. So now that's going to give us a positive, right? Two positives, or sorry, one positive, one positive, one positive. So this is going to be positive, and sorry, I didn't write this down, but local max is concave down. This is going to be concave up. So now we have to do a point between negative 0.69 and 0. So we'll just choose negative 0.1, right? And I'm going to come back and erase all of these. Stay on track. Okay, so negative 0.1, this is going to be a negative again. Negative 0.1 cubed is negative 0.1 times positive 2 is a negative. Negative 0.1 plus 1, this is now positive, right? Negative 0.1 minus 3, this is negative again. Negative 0.1 plus 0.6 is going to be a positive. Negative 0.1 minus 2.19 is going to be a negative, right? So now we have positive, positive, positive because of the two negatives, and then another negative. So this is going to be negative, so concave down, okay? So now a point between 0 and 2.19, so let's just pick 1, right? So 1, this is going to turn positive. This is going to be positive still negative, right? 1 minus 3 is still negative. 1 plus 0.609 is going to be positive. 1 minus 2.19 is going to be negative. So now we have positive, 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 and then two negatives, which also make a positive. So it's going to be positive, concave up on this interval, concave up on this interval from 0 to 2.19. So now 2.19 to 2.3, let's just plug in 2.5, right? Sorry, 2.19 to 3 is, we'll plug in 2.5. So it's going to be positive. 2.5 plus 1 is positive. 2.5 minus 3, that's still negative. 2.5 plus 0.69, positive. 2.5 plus, or sorry, 2.5 minus 2.19, that is going to change positive. And if you'll notice, every time we plug in something, that's why these points are critical points. The signs are changing at some point in this equation, right? So you'll generally have a change every time, at least one of them. So now we have, and that doesn't mean that it'll be positive, negative, positive, negative, positive, negative every time. It just means that signs are going to change, right? So now let's see, two positives, and a negative. So this is going to be negative. So negative, concave, concave down, and then 3 on, so we'll use 4, right? 3 to infinity, we'll use 4. Positive, positive, this changes to positive, 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 right? 4 plus 0.69, 4 minus 2.19, so we got a positive right here to finish it off, that is concave up. So now what I'm going to do is I'm going to erase this and copy this over here, and I'll start drawing the graph for you guys. Okay, so now that we have the graph drawn, what we're going to do is we're going to follow this. So increasing or decreasing and inflection points. So the increasing or decreasing intervals, we're going to have 3 to infinity is increasing, so I draw that. Little dash to notify that, make sure I remember it's increasing there. 0 to 3 is negative. 0 to negative 1 is also negative. And negative 1 to infinity is increasing. So then we draw our inflection points. We already have negative 1, 0, and negative 3, but we need to include negative 0.69 and 2.19. So 2.19 is going to be actually so 2.19 is going to be like right here. I'll draw it a little lower. So this is 2.19. And then negative 0.69, so we'll call it right here. Okay, so y equals negative 0.69 right there. Y equals 2.19, and those are our inflection points. So now what we're going to do, we've already, oops, yeah. So the inflection points don't affect what's increasing or decreasing, they just inflect how the concavity shifts. Remember that, I'll write it over here again, if it is positive, then it is a local min, and that is going to look like this. It's negative, it's a local max, and it's going to look like this. So negative is concave down, positive is, oops, sorry. Messed that up. Local min, not max, local max. So concave up is going to be local min, concave down is going to be local max. And that is for the second derivative. So we have, after negative 3 is positive, it's concave up. Or sorry, after 3 is positive, it's concave up, and it's increasing. So this is what it's going to look like. It's just going to look like this. Going straight up like that. Make sure this marker works a little better for you guys. There we go. Okay. There we go. So now we have an inflection point between 3 and, so 3 to 2.19, it's concave down. The inflection point flips at the equilibrium. So it's now concave down, and it is decreasing now. So concave down, decreasing, like this. And then the inflection point flips again, right? Concave up from 0 to 2.9. It's concave up, but it's still decreasing. Just like that. I'm going to drop it a little better. Just like that. Okay. So now inflection point flips again from 0 to negative 0.69. It is concave down this time, and it is still decreasing. So concave down, decreasing, and then it flips concave up from negative 1 to negative 0.69. So concave up, still decreasing. And decreasing, do you understand what I mean by decreasing? Like if it were increasing, it'd be going like this, right? Decreasing, going down. Okay, so, and now negative 1 to infinity, we are concave down, and it is it increasing? Concave down, increasing, yeah. So, okay, just like that. So now we can see what is stable and what is unstable. And there is an example of each stable, unstable, and semi-stable here. So we have at y equals 3, this is unstable because they're both away from y equals 3. So y equals 3 is unstable. Y equals 0 is semi-stable, you see, because it comes to y equals 0 at this side, but on this side it's away from it. So y equals 0 is going to be what's called semi-stable. And then y equals negative 1 is going to be our stable point. Because they both merge to y equals negative 1. Sorry, y equals negative 1 is going to be our stable point. Stable, semi-stable, unstable. Alright, thanks for watching, and I'll be back with another example on this.